Here's where we landed on total internal reflection, TIR for short. We just kind of barely got the theory out there. So let me remind you first what we're doing. Generally when you have a light that's an incident light beam, you will have that the beam splits and some of it bounces off or reflected, which is your reflected angle. We always measure with respect to the normal. And then we also have a part that refracts, and we measure that with an angle theta sub t. So I mentioned before that it's not within the scope of our class to figure out how the energy split, but just be aware that generally speaking, the light does split off into both a reflected and a refracted beam. This is the one exception that I need you to know about. And this is when you have that the light that would be refracted bends so far away from the normal that it never actually leaves the first material. So that's how we got it last time, was to realize that the light can bend so far away from the normal as to literally be 90 degrees. So here's your reflected beam, here's your refracted beam. So refracted, reflected. So this is the phenomenon called total internal reflection, where you literally have no light getting through into the second material. So notice that it does rely on bending away from the normal, so it's only possible if you're in a higher end material potentially interacting with a lower end material. Okay? So it only works if n sub I is greater than n sub t. Okay? That's the only time you can get this phenomenon. If you were bending toward the normal, there's no way this would ever work. Okay? That's why it's called total internal reflection. That's what puts the I in TIR, because oftentimes this is inside something, and then the lower NT is outside, so like your outside environment. So again, the way that we arrived at what happens here was we call that when you make the incident angle large enough, we call that the critical angle. That's when the refracted angle goes to 90, which is to say that it doesn't really enter into the second material at all. And I think I mentioned before that what becomes of this weird refracted beam that kind of slides along the limbo between the surfaces, well, it really doesn't exist. It also takes the opportunity to have no energy going into this beam. So this beam doesn't really ceases to exist instead of choosing to live in this limbo. So 100% of the light is reflected at this point, and you'll just have to take my word on that. So if you plug these things into Snell's law, you get this expression. This is how you find the critical angle. Of course, you can solve for the critical angle by itself and get this inverse sine thing, but let me just leave it like that. It's a little more compact, I guess. So what are these things? N sub t, that is the material that you unsuccessfully tried to pass into. So you didn't actually make it. You stayed in the material n sub I. Okay? So this is where you stay, and this is where you tried to go. And notice that even though you never actually made it into that material, it still does enter into the calculation, because of course that's what initiated the reflection in the first place. If you were just traveling in a single material, you wouldn't just reflect off of nothing for no reason. So that still enters into the calculation, even though it's the n on the other side that you never actually made it into. Okay? So let me remind you that the critical angle, that's just where the party starts. Okay? I showed you a demo last time where I showed you that once you've achieved this phenomenon, it will continue to be there for any angle that's larger than that too. Okay? So the critical angle is just the minimum angle required for TIR. If you meet or exceed this value, you will achieve total internal reflection. Okay? So that's just the bar that you have to clear. That's the minimum bar you have to clear in terms of a minimum angle in order to get this phenomenon. Okay? So I should say a few brief words about that. So what does the critical angle look like in different materials? Well, this is where I can remind you that if the difference in the n values is larger, then you will experience more bending. So if you have two starkly different n values, then the light will bend much more in passing from one material to the other. It'll bend more toward the normal if it's going towards a bigger n. It'll bend more away from the normal if you're going to a smaller n. Okay? So the idea is, if you look at it the opposite way, if the n values are barely different, or maybe even vanishingly not the same, then of course your bending is minimal to non-existent, right? The more starkly different the two materials are, the more bending you're going to get. Well, in this case, of course, we're focusing on bending away from the normal, because we're talking about trying to or successfully going into a lower end material. So I want to put here that in this case, in our case, away from the normal. So to give you an example, let's say that I had a slight difference in n values. Maybe I'll draw like that with a, just one letter a little bigger than the other, and then I'll contrast it with a very starkly different n value. So in both cases, of course, I'm evaluating how easy it is to achieve total internal reflection. It is possible to achieve it in both cases because the n value is getting smaller. But let's drop in a normal here. I might come in at a relatively small angle. Let's draw this. So let's compare coming in at a relatively small angle. Well, if the n value is starkly different, the amount of angle we might bend away from the normal is extreme. So something like this. So we're already almost total internal reflection. That's how extremely we're bending away from the normal. Whereas over here, the bending is not nearly as much. So here, because the bending is more extreme, we are closer to achieving TIR. And so my whole point in what I'm getting at here is that the bar to clear for total internal reflection is a lot easier to clear when the n values are different. In a certain sense, it's easier to achieve total internal reflection for a larger n sub I for a given n sub t. I should mention that the reason I'm fixing n sub t is that's usually the error. So we're evaluating, let's say this is the outside world, and we're evaluating different materials for n sub I to see how those different materials are successful or not in having total internal reflection. So it's easier to achieve it here. We're almost there right now, right? This bending so far away from the normal, it's almost recaptured into the first material. Whereas here we have a long way to go, right? Here, we would have to increase the angle significantly before this was trapped or recaptured, right? So what I mean easier, I mean that the critical angle is smaller. Remember, the critical angle is the minimum bar to clear for this phenomenon to start, right? Any angle that's bigger than that, you'll also get total internal reflection. So what we're doing here is we're lowering the bar we have to clear. The angle at which this phenomenon starts is a smaller angle. So maybe here we get, the critical angle ends up being, I don't know, 20 degrees. So any angle 20 degrees and up will get total internal reflection, whereas over here it might be, say, 50 degrees. That's a much higher minimum angle to clear. 50 degrees and up being total internal reflection, okay? Does that make sense? You can try it out in this formula. So you can put in n sub t as air, that's 1, and you'll plug in various values, and you will find that as you increase this, you will find that it lowers the bar, lowers the critical angle. Okay? You can try it and plug in numbers if that makes you feel like you can see it better. Okay? So this is where I can talk a little bit about diamond. So I mentioned at the time I was introducing index of refraction that diamond has one of the largest indices of refraction of commonly occurring natural materials. This also means that diamond is a relatively easy thing to achieve total internal reflection in. You don't need to have some massive incident angle to get it. It's fairly easy to achieve because diamond has such a large value of n compared to air. Total internal reflection is a relatively easy thing to do. And this property is actually what is used to produce the diamond's twinkle. Okay, so you think of diamonds as twinkling. They don't have an internal light source. You turn the lights off, there's no twinkling. The way that diamonds achieve twinkling is to take light that's around and totally internally reflect it through the diamond up back at you, and that's where you notice the twinkle. So I can show you an example. So for instance, let's take a look at a diamond. You have the classic kind of cut like this, kind of the more cartoon diamond. Okay? And if you just dig a chunk of diamond out of the ground, it doesn't twinkle at all because it's not cut. It's not. When you cut a diamond, what you're really doing is you're maximizing the total internal reflective properties. So let me go ahead and draw the path of an example here. So let me say I have some light coming in through the top. So here, my n sub I is the air, my n sub t is the diamond. So will I get total internal reflection here on the first when I'm going from air to diamond? Why not? It's straight in, so the angle is 0, so you always go through with a 0 angle. There's no bending at all when you go straight through. So that's one reason you're not getting total internal reflection, is that your angle isn't big enough. What's the second reason?
Larger than your n sub I?
That's exactly right. So if you did come in at an angle that's bigger than 0, you would bend toward the normal anyway, right? It's only a possible phenomenon when you're in a larger end bouncing off a smaller end, and this is not that. So we're just going to have the light pass right on through. That's how we get the light into the diamond. It just allows the light to go in there. But now, notice that the facet of the diamond is cut at an angle. That's specifically to make sure we have a non-zero incident angle. If we drop in a normal here, this is the incident angle. When they cut these diamonds, they well know what they are doing to make sure that this incident angle meets or exceeds the critical angle, right? So here, it is possible. Now, I should mention that n sub I is, of course, the diamond. So this is now the incident. I don't know where to put it. I'm running out of room. So I guess I'll put it here. N sub I is the diamond. And the thing that you're trying to go back out into is the air. So notice that the role of which one is n sub I and which one is n sub t does change. Whatever you're in currently is n sub I. Whatever you're trying to go to is n sub t. So now you're in the diamond, potentially going back out into the air. But, as you can probably guess, they make sure that theta sub I meets or exceeds critical angle for these two, for the n value for diamond. So you don't actually go back out, you bounce. So we get total internal reflection here. I don't bother to draw, of course, the light, or I don't draw the light going back out the diamond because there is none. So I just draw the reflected beam. So notice that I'm selectively chasing whichever beam is most relevant. Okay? So sometimes I choose to draw the reflected beam, sometimes I choose to draw the refracted beam. In this case, of course, there is no refracted beam. So I draw the reflected because that's all there is. Similarly, on the way in, of course, there might be some light that's reflected, but I don't care about that because if it gets bounced off the top, then it's not really relevant to the going into the diamond. So we have a second chance. We're now attempt number 2 to get out of the diamond. And the way that these are cut is that if you totally internally reflect the first time, you'll also do it the second time. Hopefully you can see from that geometry that the incident angle is exactly the same as it was the first attempt to exit the diamond, right? So if you achieve total internal reflection here, you'll achieve it here. Which means that, once again, n sub I is the diamond, n sub t is the air that it's trying to go back out into, but it will be 100% reflected. Bounces up like this. And we have now attempt number 3 to escape the diamond. So is it going to be able to get out now? Yes, because finally, we come in at a small to vanishingly, vanishing small to 0 angle with respect to normal, so now we can escape. So third time's the charm. The light totally internally reflected twice inside the diamond until it finally made a small enough angle with respect to the normal. And notice what the diamond is doing. It's just shooting the light back up right at you. So 100% of the light is able to come back up, and that's what you experience as your twinkle. So you look at a diamond with a bright light source nearby, you'll get these lights bounced back up at you in unexpected ways, and that's where the ooh, shiny aspect of a diamond comes in. Okay? Are there any questions on that? Okay, so let me show you one more example. This is also the principle by which a fiber optic cable works. So you guys when you get your internet at some point, the signal travels through a fiber optic cable, which is a cable that has light traveling through it that carries the information. Light, of course, is a great way to get information from place to place because light travels very, very fast, right? So let's take a look. What we have is a cable and air on both sides. To simplify the situation slightly, it's good enough. The cable has a coating, but I'm not going to get into that at the moment. Let's say the light's already inside the cable, so that's what it's doing inside. And we, of course, check it out. And we want to make sure if the cable has a large n value, so that's n sub I, and the air is going to be, of course, smaller, with, of course, the air having an index of refraction that's barely bigger than 1, which is the smallest value possible. So we should be able to achieve total internal reflection, but, of course, the n values being distributed that way, with being in a large n and potentially going out into a smaller n, that's not the only thing. We also have to make sure to meet or exceed the critical angle. So this angle right here has to meet or exceed the critical angle, and then we can have no light leak out. There's nothing that escapes. It all bounces. So we have the light completely contained inside the cable. And the nice thing, of course, about a straight cable is that if you meet the condition for total internal reflection on the first bounce, then you will maintain it forever. Because if you come down here, hopefully you can see that this angle that you hit the next side with is exactly the same angle that you hit the first side with. So you will be able to bounce this thing all the way on down the line as long as the cable runs straight enough. So the only potential complication you might have in having the light not be able to totally internally reflect is that someone puts in a turn in the cable that's too sharp. So say something like this. So if someone puts in a too sharp of a turn in the cable, then you can see we're coming in at a very small or even possibly zero angle to the side of the cable, and that is when we will have significant leakage. And so part of the light escapes. And that's what we don't want, okay? So we want the information to make it to the other end of the cable. We don't want it to leak out. We don't want energy loss, because that's going to mean that the signal that travels through the cable is going to be weakened. So let me try to demonstrate this for you. I have a little snippet of fiber optic cable with me here. It is transparent. You may not be able to tell that, but you can look right through it. Okay. And then I have a green laser pointer here. That's going to be my signal that I'm going to send through. I don't know how well this will turn out, but let's give it a shot. So I'll go ahead and I'll put the laser through. Now you have to understand this cable is very old and busted, so there you can see many places where along the way where you can see a little dot of green, and that's where there's enough damage that the light is escaping. But you can also see large segments that you can't see any green, right? Now the green light is going through there. In fact, you can see that there is a significant green dot on the end, right? That's where the light is finally coming and escaping. If this was a fresh cable, that's the only place you'd see the green. It would be right at the end. Okay, so you can see significant stretches still, even forgetting that parts of it are busted, where you don't see any green, and the reason why is because there it's totally internally reflected. You can't see it getting out, so there's no way you could see that if it's contained within the cable. So now I'm going to show you why there's so many damaged spots on this cable. I'm going to show you, let's find a spot that I haven't already messed up. So maybe you write, I don't know, this right here to me seems pretty clear. And I'm going to bend it, and I'm going to bend it so that I'll get some leakage where I didn't have any leakage before. So you can see if I bend it enough, you can see it gets a little bit brighter, right? Yeah? Does it get greener when I bend it? That's because now I'm getting some leakage because I'm not achieving total internal reflection right there. So a couple semesters and you get some permanent bends in there where I damage the material, okay? So that's a bit about total internal reflection, okay? Very obviously very useful application. So when you're going on a website whose server is hosted in Europe or something, why is it that you can pull up that website in a matter of fractions of a second? It's because the signal is traveling through a fiber optic cable on the ocean floor, okay? Okay, any questions on that? Did that come out in camera, or was I holding it too high? Not bright enough? Okay, well that's the nature of this, so I'll try to do one right up in front of it. That's it? Okay. So you can see the tip here, and you can see the source. Okay, let me try to put it right up here. So, am I in the camera? Okay, so if I bend it, you can get it to leak, right? You can see it? Okay. Okay. Well, to do the best I can. The production value here is not super high, okay? Okay, so that's some total internal reflection. A couple of examples of it. Just remember the basics of it. It can only happen if you're in a higher end, trying to get out to a lower end. That's the only time it can happen. And you have to meet or exceed the critical angle. That's when you get it. And then remember that if your end values are starkly different, then it starts to be easier. So the critical angle starts to be lower. So you have a lower bar to get over. Okay, the final topic in homework number 8 is dispersion. And this is where we finally acknowledge something that we haven't really talked about before. We've talked about a material having a particular index of refraction. So diamond has this n value, water has this n value, whatever. It turns out, though, that if you make a graph of the n value of a material, you can make a graph of it versus wavelength, and you'll find that something that we've assumed to be true is not actually true. Now, we've, of course, assumed that the n value is the n value. So water has a certain value, diamond has a certain value, but it's the same for every wavelength. It turns out, though, if you zoom far enough in, this isn't quite true. It actually looks something like this. So there is a ever so slight, and I do emphasize ever so slight, dependence on wavelength. So not every wavelength sees this exact same index of refraction value. If I zoom in, it looks like this. That makes it seem like a precipitous plunge, but of course you can take any graph and make it look extreme if you just zoom in really, really far on the axis. So keep in mind that if this is the visible wavelengths on the, let's say the, let's put them in, I guess. So this will be, this is in order of increasing wavelengths, so that'll be rho g big this way. Remember that rho g bib is an order of increasing frequency, so this is increasing wavelength, so we'll have to write them in reverse. The vertical axis here, this might be on the order of like 1% difference, okay? This is like when you see like graphs, you know, there's a lot of these graphs in the news right now about, you know, politics, and you'll see these extreme changes until you realize that this scale is like 1%, and that these huge changes are like nothing, okay? So this is a very small thing. It's a zoomed in version of something that's a very subtle phenomenon. But in this case, that's where all the action is. So I want to show you, just because there's a little bit of difference in the n values with different wavelengths, it can produce some interesting phenomena. Okay? Now the one thing I want to point out is that if we draw our baseline of 1, of course n equals 1 is the lowest possible. The violet has the biggest difference between a vacuum. So if violet goes from a vacuum to some material, or from some material back to a vacuum, it's going to experience the largest n change. Red, comparatively, experiences a much smaller change. Okay, so this is typically, and I guess I should emphasize this is typically because this is often materials have this sort of graph. There's some esoteric materials that do not have this graph, but typical materials such as say water or glass, things like that, they have this dispersion profile. I'll tell you why it's called dispersion in just a second. Typically, the violet light has a larger n change with respect to a vacuum, or as we talked about, vacuum and air are basically the n value is about the same. So I should say larger n change with respect to vacuum versus the other end of the spectrum, which is red. Okay. Now we of course learned that if the n value is a larger change, that also means more bending. So that brings up the mnemonic: violet bends most violently. Okay. So all colors will bend toward the normal in entering a higher end material, but violet will bend more toward the normal. And when you're going out into a smaller end material, all colors will bend away from the normal, but violet bends most violently away from the normal. So this is now taking the different colors and talking about how much does it bend relative to another color. Question?
Does that change in n value on red have anything to do with why they use red in like low light situations?
Not really. I think we'll get into that. That's a little slightly different phenomenon that you're thinking of. That has to do with the actual energy of the photons. It's sort of related, but I think that question will be much more easily addressed in a later topic. So, remember, everything bends toward the normal or away from the normal, depending on how the n value changes, whether you're going into a larger n value or a small n value, but violet always does the biggest change, because it sees if you're going from vacuum to material, it'll experience the biggest change. If you're going from the material back to the vacuum, that will also experience the biggest change. So let's take a look at something like this. I guess, let me start with something more straightforward. Let me take a piece of glass like this. Actually, I might need to make it a little thicker so it shows up a little bit better. And let me suppose I have some light coming in. And this light is going to be white light. White light has all the colors in it equally. And we're going from air, so n sub I, into glass, which is n sub t. So which way does everybody bend? Toward the normal or away? Does anyone remember? When you go into a higher end, you bend toward the normal, right? So you're going into higher end, you bend toward the normal. Which color bends the most toward the normal? Violet. Violet experiences the biggest change. So I'm going to try to draw this. I don't have a violet pen, but I do have a blue, which is the next closest thing. So everybody bends toward the normal, going from here to here, towards the normal. Red a little bit, and violet much more so. And let me complete these. Okay. So now these light beams are in glass, potentially, or actually refracting back out into the air. So that's to smaller n values. So now everybody bends which way? Toward or away from the normal? Away. So they just reverse it. So going from here to here, away from the normal. But which color is going to bend the most away? Violet. So we drop in the normals here. And what we find is the red will bend a little bit away from the normal, like so. And the violet will bend much more away from the normal. And here's what you notice. You notice that basically the fact that violet got bent more toward the normal on the way into the glass was undone by the fact that it got bent more away from the glass on the way out. So basically it just undoes the very thing that you were trying to do, or I guess I haven't told you what we're trying to do here, but if we are dispersing the colors, right, this idea that we are separating them out, we've just basically undone that. You notice that these colors were kind of fanning out here, going off in different directions, but now they're actually not. They're all still parallel. And if you have your pupil like that, if you have not gotten enough separation between these colors, if this is still going to go in, and everything in between, and then the violet light is still going to go in, you're going to still experience this as white light, right? You've kind of caused a separation in the colors, but they're all running parallel to each other now. And since this is a subtle phenomenon, the width of these colors is not enough so that you can't distinguish one color from another, so it's still white light. And you've probably noticed that when you look through a window, a normal window, everything looks pretty normal, right? So you look at white light through a window, it still looks white, okay? So what we want to try to do instead is come up with some geometry where we're not basically separating the colors and then putting them back together. We just want to manipulate the shapes so that we can, instead of separating the colors and then basically reassembling them on a parallel track, we can cause further separation on the second go. So one of the ways we can do that is by taking the piece of glass and shaping it like this. And then let's send some white light in. So we drop in the normal. Everybody bends toward the normal on the way in, but violet more so, right? So red gets bent toward the normal. Violet gets bent more toward the normal. And so we have that both colors are deflected downward toward the base of the piece of glass, but violet more so, right? So now let's drop in the normals. Now we have to consider the red and violet separately because they are, of course, now separated. So now, passing out, everyone goes which way? So they went toward the normal on the way into the glass, and then on the way out, away, right? So everybody bends away from the normal. The red a little bit, and the violet even more so. Now, notice how we manipulated the geometry here. When we wanted them, when they were on the way into this thing, bending toward the normal was downward, toward the base of this thing. And on the way out, bending away from the normal was also downward, toward the base. So we're driving a progressive wedge between these two colors by manipulating the geometry. So what we have on the way out is a significant angular spread or dispersion between these two. So we have an angular separation here. So they're heading in different directions. They're not parallel. And if you let two things that are heading in ever so slightly different directions do that for a long enough distance, right, they will significantly fan out, right? It's like if you and your friend chose a compass headings to walk that were 1 degree different, and then you walked for 10 miles, you'd be pretty far apart, right? So we can have, at this point, if someone's way over here, they might only get the red light, but they might not get any of the violet light passing through. So then they can see the colors in white light fanned out. The ingredients of white light are kind of splayed out for everyone to see. What is this thing, by the way? What is this thing called?
Prism.
It's a prism, right? A prism is just a piece of glass that is cut into a particular shape so that instead of just fanning out colors just to reassemble them, it drives a progressive wedge. Here, everyone going toward the normal is downward toward the base of the prism, but violet more so. Here, bending away from the normal is also downward and violet more so. So we have, in the two interfaces, into the glass and out of the glass, we've managed to drive a progressive wedge with what the colors are doing. Okay? So that's why this topic is called dispersion. When the different wavelengths are treated differently, that's what gives us a chance to separate out the colors and disperse them from each other. We need some kind of tiebreaker or something that allows us to take some components that are all in white light and have some of them go this way and some of them go that way. Are there any questions on this? Okay, so the final thing that I want to talk about with dispersion is how is a rainbow formed. So if you get out of physics and you don't know how a rainbow is formed, I haven't done my job, okay? So let's talk about that. Where do rainbows come from? So a rainbow comes from a very specific geometry between the sun, raindrops, and you as the observer. You can achieve this geometry in a number of ways. For instance, you can spray fine mist into the air on a sunny day, and you can see a rainbow there. There's nothing special. Has anyone ever sprayed water into the air and seen kind of a rainbow in there? Okay. So let's talk about how this works. We'll have some light, of course, coming in. The rays are parallel because the sun is very far away. And let's take a look at the horizontal light beams. And let's have one of these light beams come in and interact with the raindrop and find out what happens. So I'm going to draw a super mega zoomed in view where I'm going to approximate the raindrop as basically just a sphere. That's as good a shape as any, although as raindrops fall, they aren't quite shaped like that. So here's your white light. And again, I'm going to completely just cherry pick which beam I chase, okay? At every interface, it's possible for some light to reflect and some light to refract, but here, I really don't care about the light that bounces up because that's definitely not going to get to me. That just goes up into the sky. I'm not going to observe that. So I'm going to, of course, chase the part of the light that goes in that might eventually take a journey to my eye. So which way does the light bend going from air to a raindrop? Toward the normal or away? Just like it was from air to glass, air to water. Toward the normal. And which color bends most toward the normal? Violet. So you can draw that. Here's red bending toward the normal. Here's violet bending toward the normal. Now that they're separate, I have to track each of their trajectories independently. Let's go to the next possible time where I have to look at the interaction between, or borderline between two mediums. So this is now we're in the water, bouncing or interacting with the air. I'll drop in my normals. This. Now here, it is possible to achieve total internal reflection if the angle is big enough. I'll just tell you right now that whether or not the angle is big enough is really immaterial, because if there's any light that goes out the backside that escapes, that's not going to get to me either because I'm standing over here. So here I'm going to cherry pick looking at the reflected beam. So whether or not there's anything that passes out back here, I'm not over there. So I'm going to draw the reflected beam now. And remember, the reflection, you just reflect at equal angles. That's kind of it. So now I have my second time where I'm looking at the interaction going from water to air. So I drop in the normals here. And again, there might be some light that bounces back inside, but I'm going to choose now to draw the part that gets through. I'll tell you right now that it is generally going to escape. It is not big enough, the incident angles are not big enough to achieve total internal reflection. So going from air to water, which way does it bend? Away or toward the normal? Away, and which color bends most away? Violet. So this bends away from the normal, and this bends a little bit away from the normal. So you see we have managed to achieve some separation between the colors And let me tell you a little bit about the numbers. This is, of course, beyond the scope of the course, but I want to give you a sense of what these numbers are. This angle, which my drawing is not good, so it looks like it's parallel, but it's not intending, it shouldn't be. This angle should be about 40 degrees, and this angle should be about 42 degrees. So there's a 2-degree separation now between the colors, roughly. Okay? Now, before you look at that and say, wait a minute, 40 degrees, that's a smaller angle than 42 degrees. I thought violet got bent more violently. Well, let me point out that that's 40 degrees away from going in the complete opposite direction, right? So the violet light got accordioned, kind of bent more extremely around, and is 40 degrees away from going in the complete opposite direction, whereas red did not get bent as violently, so it only got folded around until it's 42 degrees away from the complete opposite direction. So let me try to draw that over here. I have that the red got bent like that, whereas the violet got folded much more like that. And so that particular raindrop is going to fan out those colors. Remember, violet got bent more violently. So what happens here is that the violet light comes out more horizontal, and this red light comes out more steeply. So let's take a look at what we would see from this particular raindrop. Well, these colors, of course, if they have even a 2-degree separation, that drop is very far away from you, so those colors can have a chance to fan out significantly. In this case, the red will come to you, and you'll see red in that raindrop. You will not see violet, even though, of course, violet is coming from that raindrop as well, because that's shooting over your head. It's too horizontal. Okay? So if this angle right here is 42 degrees, this angle right here will be 42 degrees. So if you look up steeply into the sky at 42 degrees, you will see red. Okay? So you don't, of course, just see red in a rainbow, and that's because there are lots of different drops. So for instance, if I go over, let's see, right about here, and look at that raindrop, that basically is doing exactly the same thing. It's also getting horizontal white light, and the geometry is exactly the same. So I'll try to draw the violet going out in the same direction, and the red going out in the same direction. I just try to exactly duplicate the previous raindrop. The only difference is that the location of this raindrop is a little bit different. So in this one, you don't get the red, because the red hits the ground below your feet, but the violet is what you do get. And remember that since this angle right here is 40 degrees, you'll see that at 40 degrees. So the entire angular width of a rainbow that you see in the sky is only 2 degrees. Of course, 2 degrees looking very far away can seem like it's very big. Okay? So if you look more steeply in the sky, 42 degrees, you'll see the red light, which is coming out more steeply because it's not being bent as extremely. And if you look less steeply in the sky, you'll see the violet, because the violet got bent more extremely, so it came out more horizontal. So since the violet, again, comes out more horizontal, you have to look more horizontally in the sky to see it. Since the red comes out more steeply, you have to look more steeply in the sky to see it. And you'll see your rainbow. And of course, I should mention that anywhere 42 degrees, it can be in any direction. So you'll see the red here, and you'll see the violet here. rainbow, you will see the red is on the top and the violet's on the bottom. Okay? At the end of the rainbow, I'm sorry to report there's no pot of gold. In fact, if you go up in an airplane and you have enough room so that the horizon doesn't interrupt the rainbow, you can actually see it as a circle. So you can look and see a rainbow everywhere around you at 42 degrees. You'll see red, and then you'll see an inner circle of 40 degrees, which is violet. Okay? So the rainbow is just a half circle most of the time because it's just cut off by the horizon. Okay? If you can get high enough above the horizon, you can see over half a circle and sometimes even a full circle. Okay? Of course, it does require that there be raindrops there as well, right? So you need, these are output by drops. So if you've ever, like, for instance, seen a partial rainbow and some mist, it's because it can't continue, right? So that's how a rainbow is formed, and I should mention that that's a good vision test because there's no property here that says the rainbow doesn't continue. Remember, this is our visible wavelengths, but this dispersion profile does keep going this way and this way. And so if you had the ability to notice, you would notice an infrared rainbow over here and a UV rainbow over here. So our eyes can only detect 2 degrees worth of this just because that's where we stop seeing electromagnetic radiation as visible color, right? So this rainbow does continue. Are there any questions on that? Yeah?
What makes double rainbows?
Right, so has anyone ever seen a double rainbow? Okay. So what happens there is that it's light that's coming through the bottom of a raindrop, and it turns out that instead of having just a single bounce off the back, it has 2 bounces, like this, before it comes out. So instead of just a single bounce, it has, every color will bounce twice. And so what does that mean? Well, you have some colors coming out like this. The violet will come out more steeply because now this is a tighter turn, so this will be violet. And red will not be bent quite as much, so red will come out like this. So notice here that violet comes out more steeply and red comes out less. That's actually the reverse of what we have over here. So if you look really steeply, I should mention these are both, you can see they're far steeper than these two, right? But which one is more steep is reversed. So if there are raindrops way up here, and that's a big if, okay, then you will see a secondary rainbow, but because the violet comes out more steep, you have to look more steep in the sky to see it. So if you ever see a secondary rainbow, the violet's on top and the red's on the bottom. The colors are reversed. So you do see these on occasion. They're fainter. They come from higher up, and so it's a lot harder to, there's a lot of more atmosphere for them to have to travel through, and because they bounce twice, that's 2 opportunities to leak some light out the backside, so there's not as much left. So that's why the secondary rainbows are more rare. It is possible to get triple rainbows or quadruple rainbows. They just start to be increasingly difficult to occur. You can look them up on the web, though, and the people have taken photos of these. Okay? So that just comes with double, triple, quadruple bounces off the back of the raindrop. Okay? Okay, any questions on that? Okay, so that's a little bit on dispersion, prisms, rainbows, things like that. It all stems from the fact that the end value is not really quite the same for every single color. All right, so you can put a line in your notes. This marks the cutoff for homework 8.